Hi and welcome to a discussion with Rohan Yadav regarding Legate Sparse, distributed sparse computing in Python. We are going to focus on specific aspects of the SciPy library in this talk and how those can be accelerated with distributed sparse computing. I hope you enjoyed. All right, cool. But then for some background, what I think would be interesting is if you could talk about NumPy and SciPy and speak to the limitations that exist with integrating these packages right now, particularly then in the context of multi-threading, and then we can take the discussion from there.
Yeah, so NumPy and SciPy are sort of like foundational libraries in the Python ecosystem. So, if you're a Python programmer who's beginning any sort of work, you often the first tool you may reach for is NumPy to just learn about multi-dimensional arrays and the wide feature set that these libraries have. You can do all sorts of scientific computing and analysis with these tools. And as we say in the paper, these tools are very flexible, but their implementation is pretty limited in terms of performance. So NumPy itself is limited to a single thread for many of its computations. Some other computations, like matrix multiplication within it, are accelerated by BLAS libraries, so they can use multiple cores. And then most things in SciPy are then also limited to a single thread. And so just to maybe make a difference, so NumPy is kind of this base library. So NumPy has just a lot of basic array operations. SciPy itself has a bit more stuff built on top of NumPy, specifically for scientific computing. So there's a variety of signal processing, sparse matrix libraries, stuff like that, all built on top of NumPy that are provided in SciPy. And so SciPy itself, often most of its computations are either written entirely in Python or like a single thread C that you have bindings to the Python code. So, of course, if you have pretty small computation, small amount of data, this is fine. The real ease of NumPy and SciPy is that you can build a program really, really fast that does what you want it to do. But then, if you start having bigger pieces of data, you want to actually run on maybe a real data set rather than just the toys data set you've been trying. You can't actually start doing that because a single CPU thread can only do so much. So the goal of this work is, and its surrounding ecosystem is really trying to take that code that you had written, when evaluating your data set or evaluating your methods, and then just take that same code and actually run it at scale. So you don't have to go through this usual process of write a prototype and then have to rewrite the whole thing kind of in MPI plus CUDA to get good performance at scale. Maybe a long-winded answer.
One follow-up question on these implementations. It's kind of surprising to me reading this paper where I see that you can only leverage sort of computations on a single CPU or a single thread for running these calculations. How come that's the case, given the extensive adoption of Python and also the extensive adoption of these packages, right? Is there a particular reason why this isn't built in already, from the start in whoever developers put together these packages to at least have wider capability of multi-threaded applications? That was surprising to me because I wasn't aware that these can only run on a single thread, at least most of the applications.
So I can't actually speak to what their goals or what they're trying to do, but I assume that for a lot of these projects, the first major piece is functionality. They really want to make sure that all these features and algorithms that people like to use are in the library. And then after that point, performance is something that comes next. And it's pretty common that functionality is much easier to achieve than performance. So you can imagine that, going to multi-threading, fine, you can expect that maybe their library should do that. But then when you start thinking about GPU acceleration or distribution across multiple GPUs and multiple nodes, there's a ton of engineering and technical challenges that go into even deciding how you're going to do that versus just implementing it. So it makes sense from a management of a project point of view, why you would stick to maybe only single thread or only multi-threading for a few operations, just because of the wide space that these libraries actually have to cover in terms of functionality. And also, scaling this stuff up is really hard. That's why it's taken, this project and others is kind of the culmination of maybe 12 or 13 years of academic research into distributed runtime systems. So it's not something you could just do from scratch. It took a lot to get to this point.
Mm-hmm. Yeah, definitely. I think if you want to accelerate it using GPUs as well, I imagine the task is significantly larger than trying to make it compatible with multi-threaded applications. That was primarily the point I was trying to get to, that single threading seems like a pretty strict limitation on what these packages are able to handle, but I'm sure there are good reasons for why it exists. Uh, Nevertheless, so switching focus a little bit more to the contents of the paper, you're looking particularly at sparse computing. And could you speak to the dichotomy between sparse computing and the rest? Why you made the split, particularly for this paper, to only deal with sparse computing, and if that's a natural split to make, generally speaking, if you want to accelerate programs like this?
Yeah. Well, so I mean, first the difference between dense and sparse computing. Like, I mean, dense computing is you have dense arrays, and sort of you have an array. And the arrays are usually like an n-dimensional array, and every element of the array holds a value. So basically, the kind of data structures that you can use for this sort of thing are sort of standard, because you just have dense memory allocations, and you can access every individual point. And the performance of computations on dense matrices is sort of relatively easy to analyze and sort of know, like not necessarily easy to get the best performance, but they're sort of, modern computers are built to sort of do dense computations pretty quickly. Sparse computations are different in the sense that it's like logically you still have matrices or n-dimensional arrays, but then a very small fraction of those entries are actually non-zero. And in scientific computations, maybe this is down to 1% or 0.01 or 0.001% of those entries are actually non-zero, which means that you have to carry out a lot of extra metadata to describe which pieces of that matrix are non-zero. And this extra metadata and the data structures and iterating through those data structures is sort of the source of all the complexity of sparse computing, especially in a distributed context, because it's kind of full of pointer data structures that are pointing to which non-zeros are actually present. In this particular work, sort of why that division exists is because NumPy and SciPy Sparse are two separate libraries. And this work builds on a previous paper called Legate NumPy, which is basically about accelerating this dense portion of NumPy. And then we're saying, this paper one is about sparsity, kind of how do you get that distributed sparse component of SciPy Sparse. But I think the real interesting part of the paper is the combination of these libraries, because most of the work is actually, this paper is not about sparse computing, and like specifically it's about how do you take this Legate NumPy library and how do you take this Legate Sparse library and make sure that they can actually run together in a way that achieves high performance, but without sort of making it this one big monolithic thing that knows everything about the other library. We kind of want to have these two libraries allowed to be developed kind of separately from each other, the way that NumPy and SciPy were. So we want that kind of ecosystem to emerge in a distributed computing environment.
Mm-hmm. Perfect. The paper that you mentioned before, we can put that in the description as well, so that people can have a look at it after. I scrolled down a little bit in the paper, and we're looking at some of the, I think, early design considerations for the library that you're looking to build. Could you speak to those and maybe what the key design constraints were for this? Like, what were the key thing for you to keep in mind as you were developing it?
Yeah. So the key decisions. The first one is kind of what I was talking about before, to actually allow for composition of the software. So in the distributed computing and multi-GPU world, it's rarely a case that, you're in the situation where you supposedly could build a distributed library, and then I could build a distributed library, and then some third person could come by and import both of our libraries and it actually works. Like, this is a very rare thing in the distributed world. And then let alone if it works, it actually achieves peak performance in some aspect. So this is something that we really wanted to be there from the beginning. Like, that was kind of a really important part of this work. And so achieving that is the driver of many of the key design decisions we did. The second one here, compiler-aided kernel generation. So something that is very specific to sparse computing is that the kernels you write themselves are very specific to the exact data structures you use. And then in the distributed setting, they're even specific to the distribution strategy you use. So if you want to come in here and actually write an implementation of SciPy Sparse that touches a distributed machine, you have to write a ton of different kernels just to implement all the functionality you need. So part of what we did was actually leveraging this prior work that I've done on a compiler for sparse tensor computations that basically can generate distributed sparse tensor computations. So rather than, I think maybe the standard way of writing these libraries is you sort of sit down and write all the kernels by hand. One thing we did was see, can we actually take this compiler and have it just generate a ton of the library for us from scratch? And that was something that really accelerated the development of the library, and it sort of allowed it to be done in a very short period of time versus the engineering work, doing it the manual way. The final one is to leverage dynamic analysis. So, I mean, we can talk about this later, but sort of allowing by having a very flexible runtime system underneath this software, it allows the software itself to be very flexible and allows it to avoid having to make a lot of over approximations that you might need to if you're not going to have some sort of precise analysis engine. So we can talk about the specifics of that later. But that was something that is very important for making this all work.
Okay, very good. One quick follow-up on the topic of kernels and the reason why you need to define those depending on the allocation strategy as well. So where does the need for this arise? If you could maybe say a few words on that.
Yeah, so I mean, for an example, so the like one such data structure for holding on to sparse matrices is called a CSR format, and it sort of organizes the row. It sort of organizes the rows in a dense way, and then within each row, it has some sparse metadata for like what are the non-zero coordinates in that row. And so your strategy for iterating over this data structure is very specific to that data structure. But then, like another such data structure you might want to use is a CSC data structure, which sort of, instead of organizing the rows in a dense way, has organized the columns in a dense way. And it turns out that the code for this is kind of different enough that you have to write a separate kernel if you wanted to iterate over CSC matrices. And in the SciPy library, there's a ton of operations, and there's at least 4 or 5 different sparse matrix formats. And so there becomes this like multiplicative cost of adding a new operation or adding a new data structure, because now you have to go add in all the kernels for that particular data structure, and this can become unwieldy over time.
Understood. Maybe we can switch gear and talk about Legion for a while as well. Would you mind introducing what that is, and then we can take it from there?
Yeah, so Legion is a distributed runtime system developed at Stanford. And so Legion is a task-based runtime system that aims to make it easy to target clusters of distributed machines. And so what does that actually mean? I think there's like 2 or 3 main interesting components of Legion. So it's a task-based programming model. So what that means is that your computation is organized as a series of tasks. So tasks are just arbitrary computations that you register with the runtime system. And so your program is described as just launching a bunch of tasks. And then to talk about data, so the Legion has this object called a logical region. And basically, a logical region is just a multi-dimensional array. It's just a tensor, whatever terminology you're used to calling arrays. And what you do is that you can have tasks that take in these regions as arguments. So a task takes in a region and says, hey, I'm going to write to this region, or I'm going to read from this region. And then the real amazing thing that Legion can do for you is that Legion lets you chop up these regions into pretty much arbitrary pieces. You can take a region and slice it up into rows, into columns, into like random subsets of that region. And then you can give those subsets to these tasks. And then what Legion basically does for you is it ensures that no matter what subsets of these regions you take, any task running is going to see that most up-to-date value of that particular region that you did. So you can have one task on one GPU on one node, like write to a particular element. And then if another task running on a different node on another GPU wants to read that same data, Legion will automatically figure out that there's a dependency between those 2 tasks and automatically move the data over from that one GPU all the way to the other GPU. And so Legion essentially lets you write programs that look like they're purely sequential, and it will extract all of the parallelism and communication from your program in order to make it look like it was actually sequential, even though that computation is run across a cluster of 1,000 GPUs. So Legion is sort of the backbone for building libraries like this that look sequential, but somehow are executing in parallel behind the hood.
Mm-hmm. So if I understand you correctly, Legion is not just something that lets you maintain references between different parts of your data structure that you're splitting up, but it also handles the synchronization of the different threads that you're evaluating this on automatically. So there's no manual interference that you would need to make in order to split that program up. It's like the split also of the data structure is also something that happens automatically, or something you would specify yourself?
So the splitting of data is something that the user of Legion tells Legion. So the user tells Legion, here's how I want to partition up all of my regions. And then Legion actually makes sure that then the necessary data is moved given the way that you've decided to partition things up. In this paper, we actually have like sort of an automatic parallelization approach that will like come up with those partitions for you and then like give Legion those partitions. So yeah.
Okay. All right. I have a figure here on an image partitioning as well that you put in the paper. Maybe we can use this for reference. So what is important to think about when you actually partition your data structures? Like, what is it that dictates whichever partition you would
Yeah,
pick?
so the partitioning is very application and problem dependent. Kind of just given a particular problem, there may be a way that you want to chop it up. For example, if I have a matrix and I want to compute reductions across each row, like one way, like the easy natural way to partition this is to partition the matrix into rows, right? So that way, no communication would need to be happen across the different partitions. Each like task on each partition can sort of just read the entire row that it has assigned to it. And thus, like this particular partitioning method is very specific to how you might want to partition sparse computations. So this image operation is one such partitioning that you could do in Legion, where this is like a data-dependent partition, where the actual partition depends on the values inside the regions themselves. So an image partition, like one way of thinking about an image is that it's like a indirection from one array into another. So I think maybe the easiest one to understand is if I look at subfigure B here, there's an array, there's a region, it's got 8 elements in it, and it's got a bunch of coordinates inside it as well, like 0, 1, 1, 3, etc. And let's say that I've already partitioned this into pieces. So each color here represents like one sub-region in this partition. And if I do an image, so I tell Legion I want this image partition to be computed, it's going to go create a partition of the destination region, D, where for any coordinate in the source, that same coordinate is going to be colored in the destination, is in the same color as the source. So there was the original partition as like 4 pieces, red, green, blue, and yellow. And so now the red coordinates, the elements in the red partition hold like coordinates 0 and 1. So the corresponding 0, 1 coordinates in the destination are going to be colored red, or like in the red subregion as well. Same for the yellow partition. It holds coordinates 2, 5, so coordinates 2, 5 in the destination are also going to be colored. And the magic thing about this is like completely data dependent. But, Legion will make sure for you that if I ever requested that yellow partition of D, like I am going to get the most up-to-date values of those elements. Yeah.
Mm-hmm. Okay, and what setting would you actually use this image partition?
So we're going to use this to partition sparse matrices. So in particular, maybe if you scroll down, if I see the CSR data format right here, so the CSR data format, it's got this list of coordinates in it. So these are the non-zero coordinates in each row that are the coordinates in each row of the sparse matrix that are non-zero. So one thing that I may want to use that image for is like if I want to multiply this sparse matrix against a vector, I need to know for all the non-zero coordinates in my sparse matrix, I need to go get those corresponding pieces of my dense vector, because those are the actual coordinates that I want to look up. And so the image relationship is something that describes that precisely, that exact relationship I need. And so some of the partitioning we do for sparse matrix operations is going to have an image from the CRD array into my dense vector. And there's an example of this, I think, later in the paper that we can come back to.
Okay, so then the image partitioning becomes, I think, a highly relevant partitioning by the sound of it, because if we're doing, for example, we're solving linear systems or we're doing just matrix multiplication or whatever, it sounds like this would be a neat approach to simplify those problems in all such cases, right?
The image is sort of the core partitioning operation for linking together. So sparse data structures are full of this indirection of here are the coordinates of this other matrix I might need. And so image is the way of relating these separate arrays together.
Okay. There's another concept of mappings. So we have tasks, we have partitions, and then we have mappings. I take it that mappings are different from the partitions. Could you elaborate a little bit on what those are and where they fit into the picture?
So, in my original description of Legion, I said there's only tasks and regions. So I never actually talked about the target machine. And so it's right that your tasks and regions, basically, you can string them together to construct this graph of the program that represents what tasks have to run when and what they depend on. And then there's a problem of actually for all the tasks that you launched and all the regions you created, you got to tell the runtime system, okay, where those tasks are actually going to run, and where those regions, where should they actually live in memory. And so mapping is this process that takes the program and actually binds those pieces onto physical resources in the device. So concretely, you could say that a mapping is like some function that takes in all the tasks, and for each task it says which processor should this task run on, and then for each region it says which concrete memory should that region actually be instantiated within. So for a simple program, if you have a 4 GPU machine and you launch 4 tasks, your mapping might say, I want to put task 0 on GPU 0, task 1 on GPU 1, and so on. And then your mapping might say, I want to take each region that those individual tasks use and allocate it within the GPU memory on the GPU the task was assigned to. And what Legion is going to do is like this mapping choice basically affects the analysis that Legion has to do. Because if you map one task to use the same data as another task onto 2 different processors, well then now, or 2 different GPUs, well now you have to put a copy between them to like move the data from them back and forth. But if you put them on the same GPU, well actually now no copy is needed because they can access the same piece of memory.
Mm-hmm. Okay, so it seems to me like that perhaps is a component that's handled automatically with the mappings. Is that taken care of automatically, or would you need to do that manually?
Yeah, so in the Legion runtime, if you're writing Legion code directly, that's something you, the programmer, need to think about. In our high-level systems we built on top of Legion, we try and do this automatically for you.
Yeah. Okay, and it feels like the tasks that you define are very important for dictating what that mapping is going to be. So maybe we can circle back also to say a few more words on tasks and how they're created. So what do you do? I assume there's a similar approach to the partitioning that actually happens in the operations that you want to run. So that my understanding is you bulk operations together into tasks, and those are atomic units more or less that you would execute, and they then get allocated to produce an optimal execution of the program. How do you group the operations into tasks?
Yeah, I think so. That is maybe a matter of taste. Usually, oftentimes in your program, usually you want to make your tasks as small as possible until they hit some minimum size, that the runtime system would actually support. And usually, maybe the rule of thumb is at least that we do in our libraries is the smallest amount of atomic computation possible. So the amount of computation that doesn't need to have any communication between different memories perhaps to perform. And so for these, maybe an easy example is for NumPy. Each one of those array operations in NumPy often get broken down into a single task. So for example, if you want to add two matrices together, well, that addition between those 2 matrices is a task. And then if you want to multiply 2 matrices together, well, then each one of those little multiplications is a task. But what isn't a task is maybe we don't make the multiplying a single element of a matrix by another matrix is not a task. That's too small. Maybe, but multiplying 2 whole matrices together is enough computation to sort of fit into a task. Yeah.
Okay, cool. So we have one big example in this paper, and I think I'm going to pull that up on screen. And maybe we can talk about the full implementation now, but if you think there are more prerequisites that we should go through first, please feel free to push back. But otherwise, we have the main figure here, and I think we can start talking about.
Yeah, sure. Okay, we can. Yeah,
your general.
Yeah,
approach.
We can try. So, okay. So this figure is pretty complicated. I definitely had many iterations of it while writing the paper. But the main idea. So this is talking about how the interoperation actually happens between Legate Sparse and Q-numeric. So if we look at the program on the left, so we basically are creating a sparse matrix, and we have a vector that we're going to multiply against it. And I have here the sort of actual non-zeros that are in that matrix. The red and blue, where ideally red gets sent to one GPU and the blue gets sent to another GPU. And I have also here the data representation of A. So this is actually the physical CSR data structure that represents that sparse matrix above it. So as we're running the program, kind of what we want to happen, if you were not using our system and you're rewriting MPI plus CUDA, what you'd ideally want to happen is that basically there would maybe be on each GPU, there's a set of allocations that hold on to the sparse matrix data and then this vector data. And ideally, we're not creating any new allocations each iteration of this program. We're sort of reusing a lot of our allocations. And the only data that needs to be moved between the 2 GPUs is just a single element from each GPU would sort of swing back and forth. if we have to move more allocations or we have to copy more data, that is kind of a failure of the system, because we want to achieve as close to that hand-tuned thing as possible. So the way it works, so I've divided this figure into two pieces. The top is, we're calling the Legate execution, which is logically what is happening above Legion. So this is like the Legate execution is doing all sorts of program analysis to tell Legion what it should do. And then the bottom is the Legion execution, which is kind of what is actually physically happening with the allocations and the copies on the machine. So I'll talk about the top first. So the Legate execution, we're running through this program. So the way that Legate works is that we basically have an we have a new library that implements all the same APIs as NumPy and SciPy Sparse, right? So as you're running the code on the left, each call to that function goes into our code. And into our code, we see that you're doing x equal a at x. So what we're going to do is we say, okay, we need to come up with we need to launch some tasks, right, to actually start up some computation. So we need to partition up A and partition up the input and output x vectors in order to do something. So I haven't shown the partitions of the x vectors. That's I haven't shown those partitions just for space here. But if you squint at the partitioning of A, you can see we've kind of chopped each of the data structures representing A in half. One GPU will use half of them, one GPU will use the other half. And then maybe an interesting part is, oh no, I actually do have the partitions of X and X1 and XO here. I didn't see that. But okay, so if we're doing a matrix vector multiply, we're going to split this up across the rows of A. So X1, the output vector, has been chopped up in half. Kind of the first two outputs of X are for the first two rows of A, the second two are for the second two rows of A. And then X0, this matrix we're reading from, so this is where that image I showed you before comes in. So the partitioning we choose is going to have an image from the CRD array into X0. And so that means that, okay, well, the blue GPU is going to need coordinates 0, 1, and 2 of X0, and the red GPU is going to need coordinates 3, 4, 5 of X0. And that's kind of shown here with this overlapped coloring in the bottom. And then so we pick those partitions.
Maybe one question there. So this is the partition representation of x0 or x1. The dimensionality of this is the same. But you were saying that in the image we are interested in, if I understood correctly, indexes 3, 4, and 5 of vector x.
Yes.
Maybe I misunderstood that, but in this representation, at least, it seems like we have 4 elements in X, or is X also somehow a sparse vector where we're doing some summarized representation of it?
So this is a confusing part of the figure, just because there's so the coordinates that I have here are actually the coordinates of the indices in CRD. The actual data is in the left here where it says data representation of A. So those are only ranged between 0 to 3. Right, 0, 1, 2, and then 1, 2, 3. So those are the coordinates of x1 or x0 that we're going to end up looking at. Yeah, I agree that this is a little confusing part of that figure.
Okay, sorry for holding it up. I just wanted to clarify. But then please go ahead.
Definitely welcome. So yeah, we take these partitions, and then basically as the Legate code is running, it sort of is going to then reuse these same partitions over and over again. And so that's maybe what we'd expect. And then what actually happens in the Legion execution is then as Legate is launching tasks away, that we're going to launch a task to do this sparse matrix vector multiply, or we're going to launch 2 tasks, one for each GPU. And you can see on GPU 0 has gotten the all the blue pieces of each matrix, each array from above, and GPU 1 has gotten each red piece. And then as we do our SPMV, then we do the norm, we get these different pieces of the matrices that we're using. And then the interesting piece that actually happens here is this reallocation step that happens in the second iteration of the program. And so this is something that Legate does, that it's this coalescing optimization, where we basically see that, okay, we have needed, for X0, we've needed actually indices 0, 1, and 2. So we need this size 3 allocation. But, and then we're also using another size 2 allocation for the same data. So what we do is we only start using this size 3 allocation. We copy all the data over into the size 3 allocation, and then we only ever use this size 3 allocation for the rest of the program to avoid kind of jumping back and forth between these size 2 and size 3 allocations, which would copy a lot of data back and forth. So instead, we sort of expand all our allocations to just the biggest piece that we need. And then we only ever use those allocations and do these copies back and forth between these bigger allocations. And this is sort of what you do by hand in an MPI program, where you pre-allocate all of these regions to just the exact size you want, and then do small copies between them. And that's sort of what we end up approaching in this program. Yeah.
Mm-hmm. And this coalescing optimization, is that performed after every iteration, or is that simply happening at certain parts of the program execution?
So it only happens after you hit a steady state in this program after once you hit the top of the third iteration. After that, no more coalescing needs to happen, because sort of all the allocations we've made are like maximal to that point.
Mm-hmm. All right. Is there anything else you want to go over in the overview of how this works? Otherwise, I'll follow up with some.
No, I mean, maybe the main
this.
takeaway is that at the top level, the Legate source program is just basically constructing a bunch of partitions, which it does automatically for you, and then it issues tasks over those partitions down to the Legion runtime system. And then the Legion runtime system is in charge of scheduling those tasks on the GPUs, and in charge of moving the data required by each task into the appropriate place. And so that's a good mental model of how this whole system works.
Mm-hmm. Okay. How does your package interact with the particular hardware in consideration if we're trying to run a program? Because these allocations here must somehow, I mean, for this program, maybe it's trivial if we have a small matrix to multiply, but assuming that you have a very large program, I guess the constraints of the GPUs themselves would come into play as well, and you would need to somehow take the hardware into account. How do you do that currently with this setup?
I guess I'm trying to... So I mean, we, employ several, space reallocation and recycling policies. We're aware of the fact that GPU memory is limited. But we make this assumption that, if you ask for a certain problem size, we're going to try our best to put that on the GPU memory you have. If it doesn't fit on that GPU, well, then you either need to get more GPUs, or you need to maybe instead run some computations on the CPU, and there's ways of doing that. But so we're not sort of like automatically figuring out how to break up. We're not figuring out for you how to magically fit your problem into the existing GPU you have, but kind of we split your problem across the available GPUs, and if that's enough memory, your program will run. Maybe is that the question that you were asking?
Okay, I think that clarifies, assuming I got the right idea. So let's say you're providing as an input to the program how many GPUs you have at your disposal to run this program. In your library, you don't particularly care about the architecture itself of those GPUs. You simply have a reference to the amount of GPUs you have, and then you do a best effort allocation to generic number or to a generic set of this number of GPUs. And you don't, for example, take into consideration whether it's monolithic or whether you have different GPUs in your architecture. Like all of that is just abstracted away. You simply consider the amount of GPUs. That's the only summary statistic you make use of.
So that I guess I have a different answer to. So our system right now assumes that, standard to the the way that many modern supercomputers look is that each node in your program is kind of homogeneous. So you will have some number of nodes, and each node has some number of GPUs, and usually we assume that all those GPUs are like the same model of GPU. So you can imagine that you have a homogeneous pool of compute resources that all kind of look the same. This sort of thing is something that Mapper controls that you talked about before. It could be completely possible to define a different mapping strategy that perhaps is aware of the fact that you may have like 5 nodes, and then on each node actually has 2 H100s and 2 V100s. And maybe that would actually change how your distribution strategy looks. That's something that the mapper can control that, that's something we haven't done. Just because today many supercomputers don't look like that, but I know many cloud environments could look like that, where you have some nodes of like high power GPUs and some nodes of low power GPUs, and you want to balance the work between these different kinds of nodes.
Mm-hmm. Is the mapper something that's internal to your library, or something that a consumer would provide?
So in our library, the mapper is internal. The mapper is the one doing this sort of copy coalescing and resizing optimizations for you under the hood. The way that it works in the Legate ecosystem itself is that externally we were trying to write these Python libraries that look like it's just Python. But then if you, as a user, you want to come and write your own library, then what that looks like is you will write a bunch of tasks, you'll write a bunch of tasks, and then you also can write a little mapper yourself that describes how you think your library should be mapped on the machine. And that's something that you, as a Legate library developer, would have control over. Whether or not your library might expose that stuff to the user of your library is a choice for you. The choice that we made is we don't think the user should have to do that.
Mm. Okay, understood. You said that the paper here is sort of the culmination of many years of research in the field. What I would be interested in, and hopefully this figure is kind of a useful reference to point to that as well, is where the most difficult parts of this acceleration task is. Like, what is the reason why we're only now arriving at these kind of libraries for accelerating sparse programs? Which part of this figure is most difficult to implement?
In just years of time, so this section of Legion execution, so the Legion runtime system, Mike Bauer and Sean Schreikler started developing Legion, I think, in 2010. The amount of algorithms, runtime system development that was needed to actually get Legion to the point where, Legion obviously handles much more sophisticated programs than the one at the bottom, but to get Legion to the point of where it was actually able to be used in libraries like this, kind of reach the point of mature software development, was around 10 years. And then at the same time, stuff going on, like at the top, we're doing all sorts of automatic parallelization for the user. That sort of research had been going on, I think, since 2019 in our group. And then as well as actually thinking about sort of structured ways to map these sparse tensor computations onto this program model as well had been something that had been happening since 2021. So there's a lot of things going on all at the same time that kind of end up at a place like this. But in terms of course, the things that the most time was spent, definitely inside of Legion. Just the amount of features that had to be accumulated to allow you to run these task-based programs at scale and do all of this analysis well.
Mm-hmm. How accessible is Legion to outside of Stanford? I think you said that it was Stanford developed originally. Are there the landscape? Is it competitive in the sense that you have many players and that Legion is one choice among many, or is it the dominating I don't know what to call it, hosting platform or infrastructure to perform these kind of tasks?
Yeah, so first I think Legion is a public open source project that it started at Stanford, but since then has been something that has been run by people at NVIDIA, Los Alamos, Slack Labs, and several more institutions. And so it's a public project. You can go use it. There's a ton of people who do use it. Definitely more in the scientific computing community. It is, in the end of the day, it was originally developed for scientific computing. So it's not going to be something you sort of think about when you think of right now of cloud-based systems. But it's definitely there. It's a low-level system, so it is. It's not the easiest to use to start because it kind of makes you think about all this stuff about distributed execution that maybe you weren't thinking about at the beginning, and you sort of have to come to terms with all of that. So it's definitely a cool thing that you could go try today. In terms of where it fits in, I think with a lot of other systems, there are many task-based runtime systems I think developed kind of in academia by industry. Some scientific ones you might have heard of are like Parsec or StarPU. Some more familiar ones you may have heard of in the Python community are maybe Dask or Ray. And I think that all these systems just are living in a very big space of design decisions that that affect whether or not who uses them, how they get used. I think Dask and Ray are something that are meant to be very Python native, and the amount of analysis they do for you is less than what Legion does. But at the same time, they're much easier to use than Legion, say. Systems like StarPU or Parsec maybe offer a different kind of dependence analysis than what Legion does. They're sort of different, offer just different things. And a lot of these systems, I wouldn't say there's one just clear winner in the world. They all kind of offer different things, and maybe depending on what your needs are, you may want to pick one over the other. So.
Okay,
But
very
Legion
good.
definitely has very many unique features. In particular, its dependence analysis was critical to doing this kind of work, and it's very unique. That is one very unique aspect of Legion compared to a lot of existing systems.
Okay, could you maybe say a few more words on that particular point?
Yeah, so this ability, Legion dependence analysis, in particular, this ability to say I have these regions, and then anytime I want any value inside that region, like I want coordinate XYZ in my region, I can just get that always, and it's up to date efficiently. That is something that no other system can do. A lot of systems have either they do more restricted kinds of analyses where you're not allowed to partition up your data into different forms, or they don't actually allow you to write to individual components of your data. Many such systems say, oh, you always have to create new pieces of data. You can't ever modify an existing piece of data. Or you can't take a region and chop it into two overlapping pieces and then do operations on those. That sort of thing, Legion can handle all of that, and it's very important for actually doing NumPy-like workloads. Like, for example, it's very common in NumPy to take an array and slice it into two ways, and then just start doing stuff on those slices, even if those slices overlap with each other. And this is something that Legion can handle, from the beginning. It was able to do this, and that has been a very important part of actually getting the software to work and have it work as efficiently as it should.
Yeah. All right, thanks. Let's then switch back to SciPy Sparse. I would like to talk about coverage for the implementation that you've now provided of the library. So I think there's a reference that there's 492 estimated functions in SciPy Sparse, and that you implemented, or that the prototype now implemented 176. Could you talk about the different approaches that you took in the implementation? I'm talking about distall, etc., for generating the solutions, and kind of why you chose different approaches there.
Yeah. Do you mind scrolling down to that section of the paper just so I get some of the numbers correct?
Right.
Because I don't remember the numbers anymore. But so there were so in the library in SciPy Sparse, I think there's three main buckets of functions there. So I think the first is kind of core tensor algebra that you could express sort of in Einstein summation notation of what this tensor computation is doing. That's things like matrix vector multiply, matrix multiply. And all of those kernels, those are sort of key performance sensitive kernels that your library has to support well. Those kernels are also the kernels that our compiler Distal knows how to generate. And so for those kernels, we use Distal to just kind of spit out a bunch of the code for us, where I don't think there's enough time to go into exactly what Distal does, but at a very high level, you give Distal the Einstein summation notation of the computation you want to perform, and then you give it a little optimization recipe that says, here are the optimization, here's how I want to distribute it, here's how I want to optimize the loops inside of that thing. And then Distal generates all the low-level code that you don't actually want to write. So in that sense, we use Distal for all the tensor algebraic kind of computations to generate us a ton of code, and then we maybe went and edited it a little bit to actually fit within the library. The second class of functions inside of SciPy Sparse, I think, are maybe more aggregate functions. And I would think of things like linear solvers or something like that, where you're writing a piece of code that is actually just built from existing functions inside SciPy or maybe in NumPy. So for those computations, this is where, one thing that we really want to do is this composition, right? We want you to be able to have this drop-in library where then you actually use the other pieces of it in a way that is you don't have to care about how those are implemented. And for these functions, this is where that requirement really shined. Because what we could do is we could just take the, for conjugate gradient or something, that has an implementation in NumPy and SciPy already. And that implementation just kind of uses all the APIs that are already built. And so we can literally just take that code and then slot it into the library, and it actually just works with high performance because of all of our effort in making sure those individual operations compose with each other with high performance. And so for many of these aggregate functions, I don't know the right word anymore, that's kind of the strategy we did. And then there's a final set of stuff which are kind of auxiliary utility functions, maybe stuff that extracts a diagonal from a sparse matrix that are sort of one-off things that don't have a very structured representation. I mean, for those, we went and wrote a little CUDA code ourselves to, we launched some tasks, and inside the task is some kernel that we wrote by hand to actually do that computation. But our whole sort of library approach allowed most of these things to fit into the first or second case. And as such, we're able to rapidly develop the library. I think I did a lot of this work as an intern at NVIDIA Research. And so most of the stuff was actually done over a 12-week period of time, which kind of gives you a sense of, to me, that's way faster than it should be to develop like a distributed, accelerated SciPy Sparse implementation, just because of the breadth of the API. The kind of key design decisions along the way accelerated that process to be much quicker than it should have been, I think.
Yes, agreed. And maybe we can talk about the remaining 300 or so functions in the library that weren't implemented as part of the prototype, at least. Is the main reason for that simply a matter of time, or is it something else that's potentially limiting the ability to onboard those as well onto this library?
Yeah, so some of them are just a matter of time. There are some matrix formats, like the block sparse row format, that in theory, the compiler still could represent those. We just didn't get around to implementing them. In theory, we could. We just didn't do it. Many of them are things that are sort of inherently sequential. So there are data structures like, I forget, like list of lists that use for sparse matrices, and they're built by all the operations on them, or they're very like shared memory kind of data structures that don't even translate well to multiple threads, let alone multiple nodes. And so for many of those computations, we decided just not to bother including them. That's kind of, the point of this library is to give you performance at scale. And it's like, we cannot parallelize this inherently sequential data structure. That is something we're not going to consider doing. Yeah. So that was a good percentage of the library.
Okay, cool. We are very short on time, and we haven't even looked at the results yet. I would ask if there are any particular results that you think are critical to present. Granted, the paper will be in the description, so people can have a look at the graphs and stuff like that in their own time. But if there are some summaries that you would like to give on a high level for the results.
Yeah, maybe scroll down, and there's just maybe one such, or maybe two such ones I'll talk about quickly. If you scroll down to figure... yeah, we can just start with figure 9, I think. So figure 9, this is just a conjugate gradient solve. It's a pretty small program, but the interesting thing is we've compared against a bunch of different systems here. And so the point of this figure is to show you that, this is like a pure Python implementation. So it just looks like you're writing the normal Python code. But the performance delivered is actually very close to hand-tuned systems. So we're achieving very similar performance to CuPy. So CuPy is a library that basically takes NumPy and SciPy code and runs it on a single GPU. So it's same way as drop-in, but it only runs on one GPU, not like clusters. And then PETSI is the system from the high-performance computing community that is built for sparse matrix operations. And so writing in PETSI, you're writing low-level MPI code, and you have to think a lot about data distribution and stuff like that. And we're able to achieve, very competitive performance with both of these libraries while giving you the same like NumPy, SciPy syntax that you're used to using. And so it is approaching this best of both worlds scenario where you get to have the nice code and actually have it run with high performance as well. So that's pretty cool. The next result I want to show is maybe this quantum simulation we did. So yeah. So this simulation is pretty neat. The performance varies at different scales. Kind of the computation itself is not very scalable, but the neat part about it is that this particular code is a Runge-Kutta method that is doing some integral. And the cool part about this is this code was sitting in SciPy and like SciPy.integrate, and I believe that it was written in maybe like 2000 or something. And that code, no one, like back then, Legion didn't exist. No one was thinking about distributing that program. But, we're able to just take it with our software, make some small tweaks here and there, and then that same code just actually ran at the scale of like 32 nodes. Without, no one thought that it would. No one was even thinking about that at the time. We were able to take that same code and run it with high performance at big machines. And so that was like a really cool piece of the research that we're able to take some real simulations some scientists at NVIDIA wanted to do and run it on much bigger problems than originally thought possible for that piece of code. So that's a cool result of the work, I think.
All right, very nice. With that, I think we should start wrapping up. The last question I would have for you is, with the results that you've now presented, if there are any directions for future research or any kind of encouragement to the community at large for things that you think require further attention?
Yeah, I mean, so we in particular have done a ton of work past this. Legate itself is now a big product at NVIDIA. We actually just released cuNumeric. I guess it's called cuPyNumeric now. This distributed NumPy replacement at SC, I think, yesterday. So that is now a public thing that you can download on Conda, and I'm not sure exactly, but other stuff is coming soon. I can't actually talk about that, but this stuff has now transitioned from a research prototype into a real product that you can run on your NVIDIA GPUs today. So this is something, if you have data analysis and data scaling needs, you'd like to continue writing in NumPy, that's something to definitely go look at. And research-wise, we've done a ton of work on just how do you actually make these programs work better, and what are optimizations you can do given that this is the way you want to organize your libraries. So we've done, there's several follow-up papers on my website that you might find there.
Awesome. Cool. So then for people listening, I'll put links to the things that we can share in the description, and then we'll round it off here. Thanks a lot, Rohan, for taking the time. I really appreciate it.
Thank you.